it's not always fun when things are too simple. Simple can get boring, right? We sometimes need a challenge. Well, so can our little number line from the last lesson. So now we will up the ante. First, let's recall something known as the Cartesian product. It involves two non-empty sets at least. All elements of first set are multiplied by all the elements of second set, and the resultant pairs get stored inside a new set. Also, these resultant pairs have every value on the left belonging to the first set and every value on the right belonging to the second set, as you can see. Let's get through this concept in more formal way. Assume we have kept a bunch of values of x in a random set, set A, and values of y in set B. Then, from their Cartesian product, we obtain not just any pairs but the ordered pairs. These ordered pairs can be represented on a graph by finite number of points, depending upon how many elements were there in each set. Got it? Great. Now, leave these little random sets and let's take the Cartesian product of the whole set of real numbers R to itself. R cross R. This big multiplication of infinite real numbers from the set R to another set R results in countless ordered pairs. And the geometrical plane required to cover such immense ordered pairs is this never-ending region. We call it the Cartesian plane or the real plane. Let's understand this the other way. Bring a real number line x prime. X prime is the left side with the infinite negative real numbers. This is the origin, 0. And then at the right side, which is labelled as x, the countless positive values from set R resides. Now, make an exact copy of this line and rotate it by 90 degrees. Change the labelling. Start from y prime at the bottom, where we have infinite negative real numbers. Go through the origin to the positive side y, where countless positive real numbers reside. Now, place the second line y prime over the first, such that both the zeros coincide. This is your real plane or the Cartesian plane. Now you can plot any ordered pair on it. Recall that every ordered pair has x coordinate on the left and y coordinate on the right, separated by a comma. These coordinates also have fancy names, abscissa for x coordinate and ordinate for the y coordinate. Like this point C, whose abscissa or the x coordinate is -4 and 3 is the ordinate or y coordinate. Plot it like this. Try plotting some other points too. No matter what ordered pair you choose, as long as its x and y coordinates belong to the set of real numbers, you can plot them on this plane. Hence, we can't run out of coordinates on this plane because both the axes that are made up of never-ending lines extends infinitely. This is not the only property of number line that follows the Cartesian plane. Just like there was one-to-one correspondence between numbers and point on the number line, every ordered pair on this plane also has one-to-one correspondence with their position, so you can't ever plot the same point at different coordinates. Such a geometrical plane on which the coordinate system has been specified is called the coordinate plane as well. Now, on the real plane, we can only plot real numbers. But what if we need to plot a complex number? Well, that requires something known as the complex plane, and we can have one by few changes on the real plane. First, change the labeling. X-axis to real axis and y-axis to imaginary axis. Second, replace the real numbers on the y-axis with imaginary numbers. And there we have it. Where did the labeling of real and imaginary numbers come from? You know it well. And since we usually denote a complex number with z for convenience, Therefore, no wonder why do we always call this complex plane a z-plane. Now that's it for this lesson. But in our next video, we will continue to explore and analyze the complexities of the complex plane. Stay tuned, friends.